Hello and welcome back. Let's talk about linear approximation. So, linear approximation is essentially making a tangent line at a point on a graph and then going slightly up that graph to a point that we might not know what the value of the function is there, but we will know what the value of the tangent line is since linear graphs are much easier to evaluate. So, using linear approximation, we can get this equation of a tangent line at a point A. And so we can find a point that we know, and that would be our point A, and our point X is the approximation of any value at that point. So, using the knowledge we have now, I'm going to draw a graph for the approximation of root 65, and then we're going to actually approximate it. So here's our square root function. Here is x equals 64. Because square root 64 is easy, that's just 8. But if we took the point 65, we went up here, we wouldn't really know what this point on the graph is. But we can approximate root 65 by adding a tangent line there. You guys probably can't even see the difference on there. The difference is so small, it's almost negligible. So, let's approximate 65 using a tangent line at x equals 64 for f of x equals root x. Here we go. So, the linear approximation at the point of 64 equals, well, our f of x is root x. So f of a is root a, and a is 64. Root 64 is 8. Plus f prime of a. Well, what's f prime of x? That would be 1 over 2 root x. You guys can double check me on that. It's just a simple power rule, but it's one you might want to memorize. So 1 over 2 times root a, which we found was 8, is just 1 over 16. 1 over 2 times 8, 1 over 16, same thing, times x minus, what's our point A? 64. So this is our equation for the linear approximation at 64 for any point. Let's approximate 65. Well, that's going to equal 8 plus 1 over 16. Our x value is going to be 65. Minus 64. Well, that's just 1, so it's 8 plus 1 over 16. Now, that's going to be 8 times 16, which I can't exactly do in my head. Let's do 8 plus 1 divided by 16. That's going to give me 129 over 16. And we'll put that into decimal form. That's about 8.0625. I'm just doing this to prove to you guys how close this really is. Root 65 is very close. Root 65 is 8.0623. Very, very close. Now, I'm going to talk to you about a little bit of insight into this here, why this is so close. We might notice the graph of x squared, the concavity of the graph decreases over time. So if we were to approximate root 2 from the answer root 1, we're going to have more error because there's this much more error here. Versus if we were to approximate root 65, let's say that's here, and there's barely any error there. And it would actually be much further up the graph because if this is 2, 65 would be way out, probably past this door. So, what can we say about this? Well, the concavity y equals x squared decreases over time. So a high concavity means a higher margin of error. But also, you can notice that this is always concave down. Always concave down means we're always going to overestimate with our linear approximations. This is just a bit over, remember? 0.0002 over, I think. If we're concave up, let's say a function that looks like this, and we linear approximation, we're going to underestimate. So those are some key points to linear approximation. But that's all it is. So thanks for watching. See you in the next one, where we're going to talk about Newton's method, and then elasticity and demand, and then we're on to the next unit of calculus and almost finished and into Calc 2. Very fun stuff. It's been a great semester. Yeah. Hope to see you guys in the next one. Thank you.